We'll go by that time. Is it okay? Okay. So I hope the first lecture was not too bad, and everyone is able to follow these lectures. Even though it doesn't look like it, the content of the first lecture will miraculously connect itself with the rest of the theory in a surprising way. So, but I think that the first lecture allows you to see already how, with your bare hands, you can already achieve quite a bit by asking proper questions and looking at power series. So today the lecture will be focusing on the modular group. A general remark: if R is a commutative ring, with identity, we can consider SL2R to be the collection of matrices A, B, C, D with the property that A, B, C, and D are in my ring, and the determinant AD minus BC is the identity element. So if you have this collection, it's a small exercise to show that SL2R is a group under matrix multiplication. So this is a general fact that we will use in the course of our discussion on the modular group. So given any ring, you can always have this construction. In our context, we will focus on SL2Z, collection of matrices A, B, C, D with A, B, C, D integers, and AD minus BC is 1. So this is a special construction applied to the ring R equals the ordinary integers. And this particular group is called the full modular group. We call this the full modular group, or sometimes just the modular group. But the problem, as you will see in a second, we're going to look at modular group and modular subgroups, and to remove any ambiguity as to which group you're talking about, sometimes the word full is used to mean level 1. The other group that will make its appearance is PSL2Z. This is just SL2Z modulo plus or minus the identity element. This will also have a role to play. And of course, there's SL2R, where the entries are real numbers, SL2R. Now, the relationship between SL2Z and SL2R is analogous to the relationship between ordinary integers and the real numbers. The ordinary integers sits as a subgroup inside the group of real numbers, but it sits as a discrete subgroup. And similarly with the case SL2Z, it also sits as a discrete subgroup in SL2R in the sense of topology. That means I can find neighborhoods of the points where there's no other elements of the group. Okay, so that is basically the preamble to what I would like to say in terms of generalities. And now I'd like to focus our attention on this particular group and its properties and its various subgroups. So typical elements inside this group are these two elements S and T. So, for example, S equals 0, minus 1, 1, 0 is an element in SL2Z, and T, which is a translation, which I use for translation, 1, 1, 0, 1, these are both elements of SL2Z. And the theorem that I'd like to start by proving is that SL2Z is generated by SNT. So, nice description. All elements of the group are words in the alphabet SNT. So how do you prove this? Well, observe that the nth power of T is just simply 1 n 0 1. So for any n in Z, that. So, and notice that T to the n applied to multiplied with the matrix A, B, C, D is just simply going to be 1 n 0 1 times A, B, C, D. If you multiply this out, you will get A plus NC, B plus ND, 0 C and D. So you get something like this. So make these observations. S squared turns out to be minus of the identity, and S multiplied with A, B, C, D is easily checked to be the matrix minus C minus D, A, B. In other words, it just flips the rows and changes the sign of the first row. So you have something like this. So with these observations in place, we can now proceed for the proof. And the proof relies on the division algorithm. So we see that first, so what do I need to show? If G is an element, I have to show that G can be written as a product of S's and T's, right? So suppose first C equals 0 first. So case 1, C equals 0. In that case, because the determinant is AD minus BC, the determinant is just simply AD and has to be 1, which implies that A equals D equals plus or minus 1 simultaneously. So that either A and D are both 1 or A and D are both minus 1. And if that's the case, so then in that case, that means we can write our thing as plus or minus 1, maybe B prime, 0 and 1. Okay, and because I told you that S squared is minus the identity, so I can write, if this is plus, there's nothing to do. If it's minus, I can put S squared, and this is a power of T. So here, this is equal to either T to the B prime or S squared times T to the B prime. One or the other, doesn't matter. And so in that case, we're done. Okay, so this is comment number 1. Comment number 2 is to use this observation here to apply an induction process. So if you have, if C is not 0, suppose now C is not 0, without loss of generality, we can suppose that the absolute value of A is bigger than or equal to the absolute value of C. That's because the transformation S applied to the matrix A, B, C, D flips these two rows around. So if one was the bigger, I can just apply that transformation in view of star. So we can suppose that in view of star. And if that's the case, then what I will do is we will, by the division algorithm, we can write A as C times some quotient Q plus some remainder R, with R less than or equal to C, strictly less than C. And then consider now the matrix T to the minus Q times A, B, C, D. You have this matrix, and that gives you A minus CQ. And well, I don't care actually at this point.
There should be R is less than mod C.
Oh, okay. So you have
Just R.
Okay. So you have this A minus CQ, and then here you have C, and then here you have D. So now I have R is less than absolute value of C, so I can play that trick again and keep on reducing this. If R is not 0, I keep on repeating this procedure until I get to the case where R is 0, and I'm back in case 1. So iterating this procedure gives us an iterative procedure which, after a finite number of steps, leads to case 1. So by applying T to the minus Q umpteen times for various values of Q, or S's in order to flip these two around, so S's and T's, you're back into this case, and then finally you're done. Okay, so that shows that that SL2Z is generated by these two matrices. That's a nice theorem in its own right. The interesting thing is, small exercise, which I will let you do, you can see that S to the power 4 is the identity element, so S has order 4. T, on the other hand, because T to the n is going to be 1 and 0, 1, it's never going to be the identity element for any non-zero value of n. Therefore, T has infinite order. Okay? So S has finite order and T has infinite order. However, here's the curious remark. S times T has finite order. S times T, so exercise, S times T has order 6. So, because I can retrieve T from S and ST, it's also the case that SL2Z is generated by S and ST. So clear thus SL2Z is also generated by and both of these have finite order. So it's a kind of a curious thing. You have two elements of finite order and generating an infinite group. And this particular observation allows us to do the other following exercise. Some of these exercises can be discussed in the tutorial in the afternoon. Yeah. So any homomorphism has image contained in the group of 12th roots of unity. That's because ST has order 6, S has order 4. The LCM of 4 and 6 is 12. And therefore, because any word with these two things will have to, this is a commutative group, so it'll have to end up in a group of 12th roots of unity. Okay, so that's pretty clear. That's how that's done. Now, we also have, which this will be useful for later work, that you can write down two elements of infinite order, both elements of infinite order. So SL2Z is also generated by, so another exercise. SL2Z is generated by T and U. U is equal to 1, 0, 1, 1. So that's a small exercise. And there's another exercise that you may want to think about for the afternoon. Suppose C, D, and N are relatively prime. N is a natural number. Show that there are elements C prime equal to C plus T times N, and D prime equals D plus S times N for some S and T integers, such that C prime and D prime are relatively prime. So this looks like an exercise in elementary. It's just congruence chasing. So you give me any triple like this, I can always find C prime and D prime such that they're relatively prime, but they're congruent to C and D mod N. That's all I'm trying to say. So this will be useful later on. Okay. So this group, the full modular group, is a very important group in the theory of modular forms. And it plays a fundamental role. In fact, its role emerged over the course of maybe half a century before any deep understanding of the group and its structure was arrived at. In our study, we will also be looking at subgroups. So this is section 2, subgroups of the full modular group. I mean, there are all sorts of exotic properties of SL2Z which I will not go into, and there are people who make their life study of just that particular group. For each natural number n, we will define gamma of n to be the collection of matrices A, B, C, D A, B, C in SL2Z such that A, B, C, D is congruent to the identity matrix okay. Now let me just pause and say that number theory, an important idea in number theory is what's called the local global principle. In order to study some large thing, sometimes it is useful to study what happens modulo primes or modulo natural numbers. For instance, if I gave you a Diophantine equation and asked you, are there any integer solutions, a first step would be to reduce it modulo some prime p and show that there are no solutions, and then therefore there would be no global solutions. Okay, so that's the idea. So this idea of trying to check local obstructions, whether there are any local obstructions, is a fundamental theme in number theory, which kind of pervades all of its modern perspective. Now this theory of modular forms is no exception. So here these groups will play an important role, and we call this the principal congruent subgroup of level M. We call this principal congruence subgroup of level M. So for example, if I have 1, n equals 1, gamma of 1 is back to SL2Z. All right. The interesting thing is that if we have, okay, well, you'll have to remember this a little bit. So here's a small exercise. The natural map so SL2Z to SL2 G mod N. So here at the very beginning I said if I have a commutative ring, I can always consider SL2 of that commutative ring, right? So here's a commutative ring and I consider SL2 of that, okay? So we have the natural map where you take the matrix and you map it to its image modulo M. Okay, so that's what's called the natural map. And you can see, you can check for yourself that it's a homomorphism. And the question is it surjective? And the exercise that I just gave before I rubbed off this blackboard, where if I have two elements C and D modulo N, I can lift them to C prime D prime, which are still congruent modulo N, but they are relatively prime. That exercise is useful to show that this map is surjective. By the previous exercise, this map is surjective. And what is the kernel of this map? Kernel is the collection of matrices which map to the identity element. But that's gamma of n, right? With kernel gamma of n. Right? And hence, I guess I'm doing the exercise. The gamma of n is a normal subgroup of SL2Z. So these principal congruent subgroups are normal subgroups, a whole family of normal subgroups, which are play an important role, and they can be identified as kernels of these things. So I will leave it to you. I will leave it to you to show that that this is surjective, and you can do that. All right. Now, just as I talked about SL2R for any commutative ring R, we can talk about GL2R. So if R is a commutative ring with identity, we can talk about this collection of 2 by 2 matrices. That's a AD minus BC. It's not 0. So these are all the invertible matrices. And you can see that SL2R sits inside GL2R as a subgroup. The question now is, for each prime P, I'd like to look at GL2. I'd like to calculate the size of GL2 of integers mod P. So I'd like to calculate this size, the size of this thing. So this equals what? And I'd like to calculate the order of SL2Z mod. So how big are these? Are finite groups. How big are they? Well, let's start with GL2Z mod PZ. So I'm looking for matrices A, B, C, D, which are with entries mod P, which are the matrix has to be invertible. Okay. Now this is where another point of view helps. The point of view, if you have an invertible matrix, another way of thinking of that invertible matrix is that the columns form a basis for the space. Okay. On the other hand, conversely, if you give me, so if I have an invertible matrix, I can take the rows. The rows will be a basis for the space. Conversely, if you give me a basis and I just make the matrix with those rows, that'll be an invertible matrix. So there's a one-to-one correspondence between bases of the vector space, two-dimensional vector space in this case, and 2 by 2 invertible matrices. Therefore, I'm really counting how many bases there are. So for the first row, I should pick a non-zero vector. So I have P minus 1 choices for the first row. Sorry, P squared minus 1 choices, right, for the first row. And then the second row, I should not pick the scalar multiple of the vector that I picked already. So P squared minus P, right? So it's P squared minus. So I shouldn't pick that multiple scalar, or any of those scalar multiples. I shouldn't pick the 0 vector for sure, or any multiple lambda of the first row, right? So you end up getting this as the cardinality of GL2. Okay. Now the the point is that if you take to the invertible elements, take the map G goes to the determinant of G. That's again a surjective map, as is easily checked by yourself. Then the kernel of this map is SL2R. So SL2R is again a normal subgroup of GL2R. And it's surjective, therefore we can use this observation to calculate the size of SL2R. So this means that this is equal to GL2R Z mod PC divided by order of Z mod PZ star, which is P minus 1. That's because, you see, GL2 Z mod PZ maps to Z mod PZ star via the determinant map. The determinant. It's a surjective map. Therefore, the kernel is SL2Z mod PZ. And the order of GL2 modulo the kernel is P minus 1. Therefore, the order of SL2 the kernel, or the order of the kernel is just the order of the group divided by p minus 1. And so that comes out to equal to p times p squared minus 1. So now we have some knowledge about these groups and their sizes. So it's all elementary linear algebra over mod p. Now, I'd like to jack up the calculation and look at this mod p squared and so on and so forth. So I will, again, leave these as exercises for, basic exercise. So essentially, solving so this is where your basic elementary number theory kicks in. You can see that by similar reasoning, we deduce that the order of SL2 z mod p squared z is equal to p to the 4 times p squared minus 1. So I'll leave that for you to do. And by induction, by an inductive argument, we can see that SL2 z mod p to the nz has size p to the 3n minus 2 times p squared minus 1. So these are not too difficult to do. This allows us to calculate the size of the group SL2 z mod nz. So suppose n is equal to product. So we have unique factorization, and sometimes we use this notation, p to the alpha divides capital N. So this notation means that p to the alpha divides capital N, but p to the alpha plus 1 does not. So that means alpha is the exact power. Alpha is the exact power of p dividing n. That's the notation. Okay. So we have unique factorization of every natural number into a product of prime powers. So I'm just rewriting it like this. And we now want to determine the size of SL2 z mod n z. And here, as you know from elementary number theory, z mod nz can be written as being isomorphic to z mod p to the alpha z, p to the alpha. So again, this is what's usually called the Chinese remainder theorem. So we can apply the Chinese remainder theorem to establish an isomorphism here as well. So we have the product of SL2 z mod like so. And because we have been successful in calculating the orders of these groups, we now know the order of SL2 z mod nz. So by our earlier calculation, the cardinality of SL2 z mod p to the alpha z is equal to p to the 3 alpha minus 2, or p squared minus 1. And so that leads us to the conclusion theorem. The size of SL2 z mod nz is equal to n cubed p divides n, 1 minus 1 over p squared. That's because if you put it all together, you will see that you have here p to the minus 2, that's 1 minus 1 over p squared, but p to the 3 alpha, so you're basically taking the cube of the number, and then you have this nice, rather beautiful result. So the order of the growth of the group SL2Z mod NZ is like n cubed, roughly speaking. All right. Now, let me say a few words about congruent subgroups. So, a subgroup gamma of SL2Z is called a congruent subgroup if gamma contains gamma of n for some n. Now, I forgot to say something. Yeah. So, since gamma of n is the kernel of the natural map So we have the natural map. You take a matrix and you reduce it modulo n. And I already remarked that this is a surjective map by 2 elementary exercises. And the kernel of the map is gamma of n. Therefore, the index of gamma of n is the size of SL2Z mod NZ, which is that. Okay, so this is the calculation of the index, and we see that gamma of n has finite index in SL2Z, and if I have a congruent subgroup, because gamma of n has finite index, so does gamma. So by this calculation, any congruent subgroup has to have finite index. Thus, any congruent subgroup has finite index. Okay. Now, one could ask whether the converse of that question is true. Is every subgroup of finite index a congruent subgroup? And that was an important question for a long time. And the answer to that is no. And that the first counterexample seems to have been given by Fricke and Pick in the late 19th century. And this is again, see, as we proceed with these topics, you will see that I'm going to touch upon really current topics of research that you can kind of branch off. I mean, yesterday's lecture was no exception, because you could take that and you can leave. You know, if the rest of the course is boring, you can leave. That first lecture is good enough to introduce you to the theory of Q series, and you can make an industry of doing just Q series and not even know anything about modular forms. People do that, so you could do that too. But here again, I want to point out that the theory of congruent subgroups is a very hot topic, and it's still topic of current research. So one can ask, if the converse is true, i.e., is every subgroup of finite index a congruence group. And the answer is no, was given by Fricka. No. Fricka and Pick. I think this guy Pick, unfortunately, was one of these people who was incarcerated in the concentration camp. So I think he died there. Anyway, it's a sad chapter of 20th century humanity. But this was done in 1887. And now the interesting thing is, if you generalize the problem, why are you considering SL2Z? What's so special about 2 by 2 matrix? You want to do 3 by 3, n by n in general. I mean, all this discussion that I have been making makes sense for n by n matrices, and we can define gamma of n, congruent subgroups, everything goes smoothly along. And it turns out that for n bigger than or equal to 3, the answer is yes to this question of, is every subgroup of finite index a congruent subgroup? And the answer is yes. The moment you jack up to 3 by 3 matrices, the answer is yes. And these are theorems due to Bass, Lazard, and Serre. So the generalization to n by n matrices, and what's called the congruent subgroup problem. The congruent subgroup problem is to determine whether any subgroup of finite index in these groups is actually a congruent subgroup. That is, it contains some gamma of n. The congruent subgroup problem is solved in the affirmative for n bigger than or equal to 3 by Bass, Lazard, and Serre. And then there are more things like generalizing it to number fields and so on and so forth. That was done by Bass, Mulder, and Serre. And there are other things like instead of talking about n by n matrices, you could talk about what are called algebraic groups, and you can define similar notions, and that's basically the work of Raghunathan and Gopal Prasad. So that's, in a nutshell, what they've been doing. They've been answering the question of whether subgroups of finite index are actually congruent subgroups. So these things are of interest because then you take your group and it's trapped between gamma of n. The smallest n that you can find is called the level of gamma. So if I have a congruent subgroup, you know that it contains gamma of n. The smallest n is called the level. Smallest such n is called level. So this word level is going to make its appearance in the theory of modular forms later on. Okay. So we'll introduce a few more subgroups. An important group is gamma naught of n. Such that C is 0 mod n. Same in SL2C, of course. AD minus BC. So this is a group. Clearly, all matrices which are congruent to the identity are sitting here, right? Therefore, gamma of naught of n contains gamma of n, right? Therefore, this is a congruent subgroup because it contains this. So this is another example of a congruent subgroup. Okay, now I'd like to calculate the index of this congruent. We calculated the index of gamma of n. I'd like to calculate the index of gamma naught of n. And again, in order to do these calculations, we use some basic algebra, essentially the first isomorphism theorem. Keep on doing that. So in order to calculate the index, we have a natural map, gamma naught of n to Z mod and Z star, given by, you take the A, B, C, and D, and you map it to D mod n. And I leave it for you to do the exercise, that this is indeed a homomorphism. Okay, so taking that lower entry and then mapping it to that lower is indeed a homomorphism. It's a nice exercise. And and moreover, it's surjective. So it's a surjective homomorphism. And the kernel of this homomorphism is equal to is equal to gamma 1 of n. Oh, sorry, I should have told. Yeah, I didn't introduce this. Gamma 1 of n. So it consists of all the matrices that go to the identity. Okay, so that gives me the definition of gamma 1 of n. It's A, B, C, D, such that it's equal to C is 0 mod n, and D is, of course, 1 mod n. That's gamma 1 of n. So because AD minus BC is 1, that means that A has got to be also congruent to 1 mod n. A, and so I could also put that down if you like. So this is your kernel, and so this gives rise to another interesting subgroup. So we have this hierarchy of groups. Thus, we have gamma 1 of n contained in gamma naught of n, contained in contained in SL2C, and gamma 1 of n, of course, contains gamma of n, right? So I know the index here, that's this calculation there. I'd like to calculate the various other indices. And this is a surjective morphism. Therefore, I know the index of gamma 1 of n in gamma naught of n. I know this index. What is it? It's equal to the order of gamma naught of n I didn't calculate. Oh, divided by 5n, that's right, but I didn't calculate order of gamma naught of n yet. That's okay. That's right. So we have that the index is Euler phi function. Is everybody okay with the Euler phi function? It's elementary number theory? Okay. And we have one more observation to make. We don't get a tea break, right?
It's after.
Oh, after. Okay. Right. So, if you have and the kernel of this, so this is again, in order to try to calculate these indices, we try to come up with proper homomorphisms and surjective homomorphisms, okay? So here we have one, and the kernel of this map is equal to what? Collection of matrices that go to the identity. But here's an additive group, keep in mind, okay? So the identity element is 0, good. So therefore, this is 0. So what does this lead us to? It has 0 mod n, rather. So it leads us to, exactly. See, so gamma 1 of n is already sitting inside gamma 0 of n. So C is already 0 mod n too. So the kernel is precisely gamma of n. Therefore, we can calculate the index to be n. So here now I've calculated. So we've calculated this index here, we calculated this index here, and we just finished calculating this index here. Right? And since I know this index, and I know this index, this thing here, I now know the index of gamma naught of n. So this leads us to this allows us to calculate the index. Thus, we can calculate the index of gamma naught of n. And what we find is this was n, and this was 5n. So that means you have to take this index and knock off n and 5n, so which equals n cubed p divides n, 1 minus 1 over p squared, divided by n 5n, right? And the 1 minus 1 over p squared factors, so this thing factors as 1 minus 1 over p times 1 plus 1 over p. Okay? And so product, you'll remember that product p divides n, 1 minus 1 over p, is 5n over n. Okay? And so this can be rewritten as n squared times product p divides n, 1 plus 1 over p, divided by n. So it's n times product p divides n, 1 plus 1 over p. Kind of an interesting function. It's kind of like the, it's an interesting function in its own right. So that's the index of gamma naught of n. All right, so that's basic background on these various subgroups of SL2Z, which will make their appearance during the course of subsequent lectures. Now, the point is that group theory by itself, of course, is a tantalizing topic, and people then study groups for their own sake. But generally speaking, the way groups arise in nature is groups arise in nature as stability groups under some group actions. So it is probably a good idea to study groups acting on sets rather than studying groups just for the sake of groups. Okay? So we will make some general remarks about firstly groups acting on sets, and then topological groups acting on topological spaces. Okay, so these are two aspects that I'd like to talk about. So groups acting on topological spaces. If you want to understand the Langlands program, this part of this lecture is the most crucial. Once you understand it and get it drilled into you, then you can see what's actually going on. So what the general philosophy is the following. So let G be a group. Let me begin with the basic things that you probably are familiar with. Let G be a group. And X a topological space. We say that G acts on X. On the left, if for each G and X in X, for each G we have a continuous map. So this dot represents the action. Sometimes we remove dots, but for the beginning of the definition, I'll keep the dots in. Such that two axioms are satisfied. One, the identity element acting on the element X should be just X. So the identity element doesn't move X, just keeps it fixed. Second, G acting on H acting on X is the same as GH acting on X. Okay, so hopefully you're not seeing these things for the first time, but in case you are, let me point out that this is not to be inferred as any multiplication in a group. Okay, so this is not some associative law that I'm talking about. This is what I have to tell these undergraduates sometimes. So these are the axioms for action. So these are the two axioms for the action. You may have seen this with G being a group and X being a set, because if you've ever studied CELO theory, I hope, you would have had to see groups acting on sets, and there it'll be just finite sets or of that nature. Here I'm just generalizing it slightly. I'm making it into a topological space, and then I want the map X goes to GX. This is a map from X into X to be a continuous map. So I can talk about continuous maps in topological spaces. Okay, so that's all I'm saying. The fact that we have this axiom, these two axioms, tells us that the map X goes to G inverse X is the inverse map. So this is actually is inverse to this map. This map. Okay, so because each of these maps has an inverse, these are automorphisms of the topological space. Yeah. Or automorphisms. So each G in G gives rise to an automorphism of X. Okay, now So you've already seen. So let me just have a show of hands. How many have already seen groups acting on sets in some algebra course? Okay, how many have not? Okay, that's a good sign. Okay, that's good. But you may not have seen groups acting on topological spaces, and that's probably the new part of this exposition. So you have the familiar notions of stabilizers then. Stabilizer the collection of group elements that fix X is the stabilizer. And a small exercise that the stabilizer of G acting on X is equal to Gx, G inverse. So this whole business of groups acting on sets is probably the main theme of mathematics. So you really have to kind of understand this idea. So we have the fixed point set, and we have the orbits. Orbit of X is just denoted Gx, collection G acting on X as I range through all the elements. So here, this is the orbit is sitting inside X. The stabilizer is sitting inside the group G as a subgroup. And the point is that we can define an equivalence relation on X as follows. We'll say two elements X and Y are G equivalent if there exists a group element taking one to the other. This is, you can verify that it's a nice equivalence relation. You know the axioms of equivalence relations follow neatly from these two axioms. So verify, exercise, verify. This is an equivalence relation. And you know that equivalence relations, you can take now elements of the space X and partition the whole space into equivalence classes. And these equivalence classes are, well, the equivalence classes are the orbits, right? Because all the elements in this thing are equivalent. So thus we get a deep composition of X as a disjoint union of orbits, some various orbits. All right. We say that if there's only one orbit, we say G acts transitively. There's only one orbit. That means so if you give any point, any 2 points, there's a group element taking one to the other. That's transitive action. So if there's only one orbit, we say G acts transitively on the space. If there's only one equivalent class, we say G acts transitively. Okay. So so in the exercises I have, just to make sure that people have seen this before, basic things about the orbit stabilizer formula and class equations and things like that, which I will maybe Karamdev can review that in the afternoon. So you have the obvious things. So it's a small exercise to show that if Gx has finite index, the size of the orbit is the index of the stabilizer. Okay, so now we are going to do one more thing, and that is we're going to look at these orbits. So we're going to use this notation G backslash X to stand for the collection of orbits. So we so this is the set of orbits. So the interesting thing is, this is the collection of orbits. So we have a natural map. So X, remember, is a topological space. And if you give me a point X, I'm going to map it to the orbit of X. Okay, that's the map. So you know that in topology, you define a topology on a space by declaring what the open sets are, right? So we would like to make this map continuous. So in order to make this map continuous, we will make sure that, in fact, we want to make sure that this is an open map. So we're going to say that we define a topology, the strongest topology on this space such that, as follows, a subset Q of the orbit space is called open if and only if the inverse image, so this map, we'll call this pi. So taking X to the orbit of X, this map, pi inverse of U is open. I mean, in some sense, I'm forcing this map to be continuous by putting this topology. That's all. So that's the idea. So this gives rise to a topological space of orbits. The orbits then can be topologized, and we can do the advantage of doing topology. We could talk about continuous functions. So this turns out that one can show that pi is then an open continuous map. That is taking open sets to open sets in that space. And not only that, it's open continuous, which is onto, so which is open continuous surjective map. So starting from a group acting on a set, if it's a topological, if X is a topological space, I can topologize the orbit space by using this natural idea. Because that's just a general comment. If in addition G is a topological group, if in addition G is a topological group, which is Hausdorff. So I hope that's okay. Hausdorff means if I have 2 points, I can separate them by neighborhood, okay, which is Hausdorff. Such that, in the topological group, you have the usual business. You have a map, G cross G into G. You have the multiplication maps. So you take these two pairs and map it to GH inverse. This map, we want it to be continuous. So we want this map to be a continuous map. Not only do we have this, so we have it to be continuous, we say G is a topological group. So if G acts on X, if G is a topological group acting on a topological space, then what we have is a map. G cross X into X given by the pair Gx goes to G acting on X. This map, we're asking it to be a continuous map. So when we have the situation where G is a topological group. Okay. So these are very general statements. Somehow the philosophy is that these orbit spaces inherit a topological structure if the group and the space have such structures. So remark, if G is a locally compact topological group. That locally compact means every point has a neighborhood which is compact, okay? If G is a locally compact topological group with a countable basis, so here's the, sorry, this is a theorem, not remark. It's a theorem, which I'm not going to prove. It's proved in Shimura's book, so reference Shimura. But we don't need to know the proof, we just need to know the statement of the theorem. The theorem is if G is a locally compact topological group that acts transitively, on a topological space X, I should have okay, I'll just put with a countable basis of open sets, with a countable basis. Then for each X in X, the space of right cosets of the stabilizer of X. So with G sub X is a stabilizer of X. I look at the right cosets of the stabilizer. This is homeomorphic to X with the correspondence G, the coset so the correspondence is, so here I'm looking at the cosets here. This coset will correspond to this point. Okay, so this is a point in X. Now, let me try to summarize what we have established so far. So you have a topological group acting on a topological space. And if the action is transitive, suppose the action is transitive, take a point x naught and look at the coset space, the space of cosets of the stabilizer group. I'm saying that this can be thought of as a space X. And the point is the coset Gx naught corresponds to the point G acting on X naught. Because it's a transitive action, this fills up all the space, all the elements. So I can identify elements of the space X with cosets. Now what's the advantage of looking at the coset space? If G is a topological group, the coset space inherits the quotient topology, the usual topology. So you can make this into a topological space. It may not be a group. You know, these cosets may not, the coset space is not necessarily a group unless it's normal. So we don't need to worry about that, but the cosets can be endowed with a topology. So this is a topological space which is inherited, the topology inherited from G. And so what happens is with this action, we're identifying the topology here with the topology on G. So all of a sudden, we're able to go from some abstract topological space X, which had no connection to G, except the fact that G acted on it. And then I can identify, if it's a transitive action, I can identify X with a coset space. Now this is what I mean by, this is the comment that you have to understand in order to understand the Langlands program. Because the generalization of the upper half space, everyone knows that the Langlands program is a generalization of the theory of modular forms to higher dimensions, automorphic representations and so on and so forth. So people learn about modular forms like you're going to be doing in this course, but then where are the modular forms in the Langlands program? There aren't any. There's automorphic representations. It's because he moves away from the upper half space by recognizing the upper half space as a quotient space of GL2R. That's basically what he does. And then once he's made that identification, then he realizes, hey, the generalization of upper half spaces are really coset spaces of algebraic groups. So then the whole theory just kind of unfolds. Okay, so this is the comment. This is the key theorem. If I have a topological group acting on a topological space and the action is transitive, I take any old point, I take the stabilizer, I look at the quotient space of the right space of right cosets, and I say that this can be identified with this. So now this X, which had no group structure whatsoever, as it were, can be, I'm not saying it's going to have group structure, but I can identify it as a space of cosets and think of functions on this topological space can be thought of as functions on G which are invariant on this thing, which are constant on those cosets. See, so that's the automorphy condition that's going to come later on. Okay, so this is the key remark to understand the whole of Langlands program. All right, so one more comment, and I think we're okay with time, right? One more comment, that is this idea of double cosets, which we can do as exercises later, but I want to introduce double cosets because they will be useful in our understanding of Hecke operators. Yeah, maybe I'll just give you an example before I continue this double coset business. So example, which is going to be the starting point for next day's lecture. SL2R acts on the upper half plane. So the upper half plane is a set of all complex numbers with imaginary part positive. And the action is, you give me a matrix A, B, C, D, and it's acting on the point Z. The action is AZ plus B over CZ plus D. And you can check now, is this an action or not? That is, if I have a point in the upper half plane, is this again in the upper half plane? You have to check that. I'll leave that as an exercise. So it acts on the upper half plane, and in fact, it's a transitive action. It's a transitive action. Okay? And my group is locally compact, and it's acting on this topological space of the upper half plane. So I can apply that theorem and say that take any point. Okay, I'll take the point I, which is in the upper half plane. Take the stabilizer of that. We'll worry about what the stabilizer is in a second. Take the stabilizer of that. So let me just call this gamma, just for now. Gamma sub I, stabilizer of I. Stabilizer of I. then the theorem is saying that if I take SL2R modulo the stabilizer of that group, I can identify this quotient space of cosets, which already automatically has a topology because this guy's got a topology on it. I can identify the space with the upper half planes. Now, in this course, we're going to talk about modular forms, which are functions on the upper half plane, which have certain transformation properties. Okay? Those are modular forms. So if you're trying to generalize the theory of modular forms, this theorem allows you to move in another direction. It allows you to shift your focus from the upper half plane to a quotient space of SL2R. Well, it's a topological, that's the point. It's a topological identification. The topology on here is the same as the topology that you get here. And that identification allows you to think of modular forms as functions of SL2R with certain properties on this. Now, as functions of SL2R, now you know how to generalize it. It's got to be GLN or SLN or higher dimensions. It's clear now how to go. But that point of view was needed, and that was the kind of lightning idea of the Langlands program. Okay, so in the few minutes remaining, let me just say a few words about double cosets. So, if you have, suppose that H and K are subgroups of a group G, then we know that we can write G as a disjoint union of right cosets, right? So you can write you give me any group, you can always write that. Then we can define a K action on the space of cosets of H. Namely K. Well, now, if you don't mind, I'm going to put it on this side, okay? It's going to be a right action. So K acting on a coset G is going to be H GK. So that's the way K is an element in K. K is an element in K. And so you can see now the orbit of the coset HG is just simply HG capital K. Is so these are your double cosets. So the orbits. So I take a subgroup H, I look at the set of cosets of H, and I can define now, take another subgroup K, I can define an action. You'll have to check this is a legitimate action. It acts on the right in this manner, and then you can see that the orbit of a coset will just simply be these double cosets. So it's a further decomposition of this, so that of this space. So if we end up getting that, for example, thus this has to be a bunch of union of, you can write this as a union of certain cosets. Okay, so those are your double cosets, and they will make their appearance in the course of the theory of Hecke operators. So that more or less summarizes my introduction to groups acting on sets, but topological groups acting on topological spaces. With that background, I think we're more or less poised to begin the study of the upper half space and modular forms tomorrow. Yeah.